Hello and welcome to Psych 319, Chapter 13, Part 1. We're going to cover a bunch of things, and this is thinking and problem solving. So how do you define thinking? Do you define it as a behavior? Is it independent of behavior? Is it something that goes inside your head? Behaviorists used to think of thinking as just merely stimulus-response reflexes, so that even the most complicated things that you do could be described as a reaction to some stimulus in the environment, and that there was nothing really going on in between those two. And cognitive psychologists would tend to think of thinking as something that goes on internal in the head. I like to think of thinking as something that happens when the stimulus and the response are separated by a really long period of time. So if there's a long enough period between the stimulus and the response, it's most likely that the epoch in between is occupied by something close to thinking, which is internal thoughts. You can also think of thinking as cognitive processes that are not automatic. So for example, a spinal reflex, if you hit your knee with a hammer and your leg jerks, that relay goes through the spinal cord, but it doesn't actually go into the brain. It's quite automatic. There are many types of thinking. There's focused thinking and unfocused thinking. Focused thinking is what you think of as thinking. Clear, objective thoughts about things. Unfocused thinking is daydreaming or unconscious processing. Your brain is still working, but it's not something that's particularly focused on one thing. So in tackling this problem, if focused thinking is directed at problem solving, then what is problem solving? A problem is a situation where the solution is not immediately apparent, just as you would imagine. And problem solving generally involves an initial state and a goal state, where you are now and what you're trying to solve. And in between there are many actions to solve the problem and get to the goal state. You can have well-defined problems with a clear goal state and ill-defined problems. Ill-defined problems can be ill-defined for multiple reasons, but one of the primary reasons is that there's no clear initial state or no clear goal state. Either you don't know where you're heading or you really don't know where you're starting out. There are many techniques to problem solving. One is called generate and test, or you can think of it as trial and error. Imagine you had a million monkeys in an infinite amount of monkeys and an infinite amount of typewriters in a room. Eventually, by random chance, one of the monkeys would type out all the works of William Shakespeare. However, it takes a really long time for that eventuality to happen. So trial and error becomes difficult if there's many possibilities to test. So it's always a trade-off between the effort it takes to do something and the amount of time you have. So in solving a problem, generate and test will work if it's not very expensive to test a bunch of different options. But there's some things you can't do, like you can't become a doctor and then try a new career and then try a new career and cycle through around 10 careers before you decide you really, really like something. That takes far too much time. Another problem-solving technique is called means-end analysis. So ask yourself, why doesn't Ben & Jerry's have a liver and onions ice cream flavor? Well, part of the reason is you can probably imagine that doesn't taste very good, even if you've never ever tasted it before. And the reason is you have the ability to predict the future using your frontal cortex. Your brain basically decides based on its previous experiences what it thinks liver and onions ice cream would taste like, and then decides whether it's not working to that problem. So what you're doing sometimes is visualizing the many possible solutions to a goal before actually acting on that or trying to execute a system to get to that goal. And of course, again, the frontal cortex is necessary for this because it's involved in predicting the future. So one of the interesting side notes is that frontal cortex is still developing in teenagers, which is probably why many teenagers do very, very risky things like skateboarding and various stunts, and that's why teen pregnancy might occur and why kids smoke and drink a lot, is because they're not really aware or looking into the future as to and analyzing how all these things will affect their lives. So here's just a funny example of that. It might not actually show up, but an average teenager doing a silly thing. Looks fun in the moment, but if he had predicted the future a little bit better, he might have realized that sometimes when you do stuff like this without any, uh, yeah, tree, ouch, yeah, sometimes it can arise in disaster. Fortunately, he's okay. He made it through that one. Another problem-solving technique is working backwards. So think, if you wanted to become a circus performer, you might not know where to start, but you might know where your goal is. Let's say you wanted to be the person who is on the 1, 2, 3, 4, 5. Let's say you wanted to be the fifth person up here. You wanted to develop the skill to be able to take that trampoline or teeter-totter all the way up and land on the top rung. Well, how do you do that? Well, you might think of it as working backwards. You know what the goal state is. You want to be number 5. So maybe to get there, you practice being number 4 and practice being number 3, and before that, number 2. And eventually, you'll hopefully get the skill. So sometimes if you can see the end of where you want to go, you can get there more easily. It can sometimes provide a more direct path. Think of this when you're thinking about your career. A lot of students go to school and then they decide what they want to do. But if you decide what you want to do first, it makes your education a lot more direct. You'll tend to take classes and things that directly apply to what you want to do. Another method is called backtracking. So when you're trying to solve a puzzle, oftentimes you make a mistake and you have to go backwards in time. So memory is a huge component to problem solving because it allows you to make corrections in your course. A crossword puzzle is a perfect example of that. We always make mistakes in crossword puzzles and have to go backwards and correct things. We've seen in previous chapters how bad our memory is, so if you're trying to solve a difficult problem, it's best to write things down on pen and paper, and it'll allow you to backtrack and solve the problem a little easier. Sometimes you can use technology, like computers are very good extensions of our minds, and they help us keep track of the many things we need to do. Another problem-solving technique, which is really important, is called analogy. And this is an example of the hydrogen atom and the solar system. And so when Niels Bohr was trying to figure out the structure of the hydrogen atom, he was thinking about the way the planets were aligned, and that how you could have various planets circling the sun, and that's what allowed him to come up with the conclusion that electrons are traveling around the nucleus of an atom at various orbits. And so he took something he knew and by analogy applied it to something he didn't know and solved the problem. And this is a very, very good way of solving problems, and it's also sort of a path to creativity. I'll skip over this here. Now that we have these problem-solving methods, it's important to talk about blocks to problem solving. So take a look at the figures to the right, and what do you see? Most people will probably say they see the numbers 12, 13, and 14. But there's this thing called mental set. Sometimes we have an inability to look at a situation from anything but one perspective. You see 12, you see 14, so the logical conclusion is that the number in the middle is a 13. But you could also look at it from another perspective. It could be A, B, C. Perceptual set is the tendency to perceive new stimuli as similar to the stimuli that came before it. So take a look at this figure here. Do you see the Dalmatian? There is a dog hidden in this figure. Some people might see it, but if you don't see it, you're probably going to have a hard time finding it because you've already decided what elements of this figure are foreground and background, and it's going to be difficult to figure out. This is the nose, this is the legs, and here is the back. Functional fixedness is a variation of these two. It's an inability to perceive a novel use of a tool or a new way of doing something. So if you've ever tried to use a butter knife as a screwdriver, you've managed to solve a problem in a creative way. You use a tool in a way it wasn't intended to solve a problem. When you're functionally fixed, you wouldn't be able to come to that solution. You would look at the screw and you would look at the butter knife and you'd say, well, I guess I can't turn the screw, because you can only think of a knife as a knife. Here's an example from an artist, Jen Stark. She came up with a very, very simple idea of creating sculpture out of paper. It's hard to believe that this hasn't been done before, but she was kind of one of the first people to sort of realize that you could do novel things with color and cutting paper up, and has built an entire artistic career around it. Sometimes we have blocks of problem solving that involve incomplete or incorrect representations of things. Sometimes if you make an assumption about how a situation is or how a tool can be used, it might lead to a misunderstanding of the problem, and then you might lead to a faulty conclusion. Sometimes also you can have a lack of expertise. It's going to be very difficult for you and I to figure out a problem that has to do with the space shuttle, because neither of us are physicists or have that particular experience. Experts in a field have an ability to see deep relationships where novices tend to focus on superficial appearances. So when you're trying to solve a problem, there's something that we call the problem space. So remember that we have an initial state and a goal state in our problem. And in between there are a number of ways to get to from the initial state to the goal state. I'm going to show you a famous problem called the Tower of Hanoi problem. In the Tower of Hanoi problem, the goal, if I get this right here, you have 3 rings and you're trying to move them from A to C, and you can only move them one at a time. And they need to be in the same order that they started. And so it's kind of a difficult problem, but there is a discrete solution to it, and it involves about 7 steps. The goal is to solve the Tower of Hanoi problem as quickly as possible. And right now you can see it's working, the solution in front of your eyes. Now, that's the actual solution. And if I'm to draw that out on a map, you can see that here's the solution from the starting point to the goal. And this entire space here is called the problem space. There are many ways of getting to the goal, but the shortest path involves 7 steps. The interesting thing about a problem space is if you give somebody the Tower of Hanoi puzzle, but you don't give them the task and you allow them to play around with it, they tend to solve the problem faster when you give them the problem, compared to a case where you just give them the Tower of Hanoi puzzle and tell them to solve it right away. And the take-home lesson from this is that if a person is allowed to play in a problem space without any constraints or goals, they learn the space, they become an expert in that domain, and this allows them to solve various problems more quickly. You can think of this as applying to your education. In your education, we have students study very broadly. You study multiple different topics, and the reason is not because we're trying to waste your time, is that because if you study various fields of knowledge, you're more likely to be able to solve the problems in your own field better. So at every stage in the process, you're likely to use several problem-solving strategies: means end, backtracking, trial and error, maybe working backwards if you get stuck. And each strategy requires a different level of engagement from multiple brain systems, including short-term memory, long-term memory, the frontal cortex, and so on and so forth. Yes, this is something we just talked about. So how come it's difficult to understand expertise? What makes experts good at what they do, and why is it so difficult to achieve it? Experts have a lot of knowledge, and with that knowledge comes vocabulary. If you think about language, language is a way of describing very complicated concepts in a very efficient fashion. So an expert can say one word and it has a lot of meaning for that person, and a novice has to learn what that word means. Even using everyday vocabulary, experts have more efficient means of representing information. We are all, humans are very good pattern recognizers. we can quickly identify a solution based on context clues in the problem. A doctor can quickly identify a tumor on an MRI much faster than a computer program can. A chess player, for example, can look at a pattern on a board and it can solve, and that chess expert can determine how to win the game in a brief number of moves just by looking at the board. This involves a process called chunking. Chunking is representing a large bit of information into a simple word. So for example, a chess player might be able to represent 14 or 15 moves using a single concept called the Queen's Gambit strategy. A chess player can look at a board and say, okay, if I use the Queen's Gambit strategy here, I can win the game in 14 moves. Okay, so one of the differences between experts and novices is that novices tend to focus on the individual steps. They don't know how to, or they don't have the experience to encode multiple complicated steps into one simple idea. Think about when you learn how to drive. When you learn how to drive, there are several things you do in different parts, putting in the clutch, stepping on the gas, shifting. But an expert just says, oh, I'm going to turn left, and all of those things happen automatically. So we can apply these things to creativity. What is creativity? Well, it's just problem solving. Remember our butter knife example? That is a creative solution into screwing a screw into the wall. So many solutions to problems are not considered creative. They're just solutions. Creativity is usually considered a novel or unique approach to solving a problem. However, creativity is not synonymous with artistic. We usually call artists and musicians and so forth creative, but not all artists or musicians are creative. So there are artists without original ideas, and there are artists who create a completely new idea. Either they write a song or they create a new way of writing songs. So for example, Jimi Hendrix, the famous 60s rock and roll guitarist, invented a new chord. And before him, all the rock and roll before him hadn't even thought of this chord yet. In fact, all of the classical music before them hadn't even thought of this chord as well. And the Beatles invented many things that relate to music. They invented multi-track recording. They invented early synthesizers. They invented a lot of techniques that eventually became common to recording music. So that's creativity, coming up with something completely new. They generally say there's 4 stages to creativity: preparing, kind of idealizing what the formula, what the problem is, figuring out what the problem is, thinking about it for a while, and then suddenly, after working or thinking about it, you get this illumination, you sort of achieve insight, and then you test your hypothesis and see if it works. If it doesn't work, you go back to square 1 or 2 and try other things. People think, oh, well, I can't be creative sometimes, that you're either born creative or you're not. And that's not true, because creativity is nothing different than problem solving. It's very much possible to train people to be more flexible in their thinking and to score higher on tests and solve puzzles and think more deeply about issues. Just by learning about this creative process right now, you will be a more creative person in the future, because you understand that creativity is just another example of problem solving. Training doesn't necessarily produce highly creative individuals overnight. It does take practice, but it can be enhanced. You develop a knowledge base about a problem, you create the right atmosphere for creativity, you search for analogies. So dare I say, this is how you might consider to be a creative person. Free yourself from the blocks to problem solving. It's very important. Don't allow the blocks we've talked about to get in your way. Allow yourself to conduct unfocused thinking without critical thinking. If you become too critical, you inhibit brainstorming, and brainstorming is where creativity where creativity happens. If you're allowed to put a bunch of crazy ideas on the table, one of them might be the right solution. So if you brainstorm first, this provides several ideas that you can evaluate critically later. So it's a 2-stage process: brainstorming and then critical thinking. Most artistic creativity is just hard work. Stevie Wonder said he wrote a song a day. He woke up in the morning and he writes a song a day. And a very small proportion of those songs are what he would consider good that he shows to the public. Cirque du Soleil, the famous circus troupe that travels the world, they rehearse 17 hours a day. They work very, very hard. It's no different from solving problems in math, in your education. It's just applied artistically. Charlie Parker changed jazz, it created a whole new language for jazz, and he practiced 15 hours a day for 4 years. It's a lot of work. They always say it's 99% perspiration and 1% inspiration, right? I'm going to skip all of this stuff because you can take a look at this in the notes. I'm going to explain this one example, though. It might be something that's fun to try. A lot of people feel they can't draw, but sometimes they're approaching it differently. So this is an exercise. I want you to try this. Try draw this figure. I know it's upside down. And by putting it upside down, what happens is it forces you to focus on the lines rather than the bigger picture. And if you put it in a grid, I'll bet that if you grid your paper just like this is, that you'll be able to do this drawing almost perfectly. It allows you to focus on two things that you can do already: see and draw. You can draw a straight line. You write. You have the physical ability to draw and make lines. You have the ability to see. What this exercise does is it trains you to see in a new way. And that's really what artists do. They train and practice to see things for what they truly are, rather than what they think they are. And that's what allows them to become great artists. All right, I will see you in the next chapter.